What I would like to do in this lesson is to look at how the geometry of an object that moves down this ramp will affect the movement of that object down that ramp. In other words, I want to look at the forces that are acting on it and see how that affects the acceleration of the object. Okay, now what we're going to look at is, as the objects move down, are they separating? If the object in front gets down first, then it has a larger acceleration. Okay, so first of all, this is a ramp. There is friction on this ramp. These carts have wheels and they're rolling down the ramp. Because they are rolling and these wheels are very light, because they are rolling, even though there is friction, friction is not doing any work on the object, and so therefore it's not robbing the system of any energy. Some of you will be learning about energy later, but most of you do know about energy. If I take this object and just slide it across this table, the kinetic energy, the energy due to motion that it has originally, gets robbed by friction because of the friction between the surface and the cart. Okay. If, on the other hand, I have these wheels and I roll it on the wheels, it'll roll for quite a while, because even though there is friction, the point of contact of the wheel with the ground is not doing any work. The point of contact is not moving with respect to ground. As it rolls, if I take this roll of tape, as it rolls, the point of contact here is not moving up or down the ramp. The next motion of this point right at the bottom is going to be vertically upwards as it rolls. So therefore, friction is not doing any work. Work would require a force acting over a distance. Although there is a force of friction, it's not acting over a distance. It's acting at a point which is not moving. Okay, so these two objects have the same mass. As I put them on this ramp, they will roll down with the same velocity at each point, which means they have the same acceleration. So if I release it from up here and I let it go, they go down at the same speed. There's no separation here between. And just to show you that there isn't, I'll rotate it so you know that you can see both directions. It's not like one pushing the other. They both still come down at the same rate. So they both have the same acceleration. What forces are acting? Again, there's friction, but that's not doing any work. There is the force of gravity, which is down, but there's a component of gravity down the ramp, which is what's making it accelerate. So the component of gravity down the ramp is what's causing it to accelerate. There's also the normal force, but that's being canceled by the component of gravity that's perpendicular to the surface. So therefore, these two guys come down with the same acceleration. Now, the next question is, if these had different masses, right? If this one was heavier than this one, or this one was heavier than this one, would they come down at the same rate? All right, so here, these have the same masses, or they're identical carts. I will add a heavy mass. This is a kilogram. So I'll place a kilogram on here, and some of you said that this would come down faster because it has more mass. Some of you say this would come down faster because it has more mass. So let's try both out. If I release it from here, they come down at the same rate. So they have the same, at least it looks like they have the same acceleration. Just to make sure, I'll put it on this side. And in fact, the acceleration does not depend on the mass of the object that's coming down the ramp. Okay? Just like if you jumped off a building, and you jumped off the building with somebody that's lighter than you or heavier than you, you will hit the ground at the same time. If you go on a swing and you swing side by side, you're in the middle. You have somebody heavier on this swing, somebody lighter on this swing, and you swing with the same rate. Okay, because of the mass will cancel out when we look at the force, which is going to depend on the mass, is going to the mass and mass times acceleration. So the force, which has a mass in it, is equal to mass times acceleration, which has a mass in it, and the mass cancels out. Okay, so these two guys have the same acceleration as they come down the ramp. Now let's compare that with some other objects. I use this to start the object coming down. because it's easier to get things to be lined up. So I have these round objects here. Let's look at this. This is round. This is not. And I release it from here. Which one is going to come down first? Okay, and let's do it this side, just so we see it. If I release it from here, it looks like they come down at the same rate, but in fact, it's being pushed by this one. If I turn it around and release it like this, you can see that the acceleration of this was larger than the acceleration of this sort of semi-cylinder type object. Okay, this is actually a hanging weight. You'd hang it from something and use to use in some experiments. Okay, so let's look at how the geometry of the object sliding down affects the motion of the objects as they roll down the ramp. Okay, now this basically goes down because it's friction free. Again, no friction is acting here, so it rides on these wheels as it rolls down. So the acceleration of this is basically g sine theta, where theta is this angle down here. So this would have the acceleration of this is g sine theta. Now let's look at these other objects. Here I have a plastic solid cylinder, and I place it on the table. We saw that this round thing is going to lag, right? This has a larger acceleration than this one does, so this has a smaller acceleration. There is what is causing that to fall behind, okay? And we'll come to that in a minute as we look at these different objects. This is a solid cylinder, uniform throughout, and I place it here, release it, and you will see that it falls behind, right? The acceleration of this is smaller. Similarly, this is a metallic, much heavier, longer, also solid cylinder, and I release it from here. It comes down again with a smaller acceleration than the card itself. And my third object is a hollow PVC pipe. Okay, I release that, and you can see it goes. The acceleration obviously is a lot less. So let's sort of, what's the difference between these? Obviously, the difference between these are, one, they're about the same size, but one is hollow and one is not. So let's compare things that are the same shape. These are both solid cylinders. One is much longer. Both are solid. One is much heavier than the other. Okay, so let's try and see what happens here. Of these two, this one's heavier, this one's lighter. This one has a bigger radius than this one, as you can see. But which do you think will come down first when I release them from the same height? Go ahead and put your answer in the chat. Are they going to be a tie? Is the lighter one going to, the plastic one going to come down first, or is the metallic one going to come down first? Okay, so we come back. And now that we're back, we're going to see if you were able to predict which one will have the larger acceleration or a smaller acceleration. Lo and behold, they have the same acceleration. Okay, so somehow, even though these are very different things, the shape of these, this is a bigger radius, this is a smaller radius. They're both, one's longer than the other. They're made of very different materials. This is very, very light plastic. This is heavy metal, okay? But they have the same acceleration. How about these guys? Okay? These are about the same length. There's a lot more plastic here. I mean, this is still a little bit heavier than this one is. And if I put these guys together and release them, you will see very different acceleration. This has a much lower acceleration than this one does, okay? And what's the overriding factor? Is the geometry of the shape. This is hollow, this is hollow, this is solid, okay? So they have very different consequences in how the object rolls down the ramp. And these guys are rolling, just to reiterate, these guys are rolling It's not sliding, it's rolling. And it's rolling without slipping. So there is no force of friction that is doing any work. So the acceleration here is purely due to the gravity acting on this and pulling it down. So the overriding factor is the geometry. Just to give you another hint as to what's going on, let's sort of put a combination of all these guys together. Right, these are, let me try this first. This is solid metal, this is solid metal. Where's my center? Oh, I lost my center. If I release this, and I'm doing this suggestively, you should be able to see that this one, which is not hollow, okay? This is not hollow. This is a solid cylinder, as is this. But the geometry here, look, I mean, they are very different. I mean, this is a solid cylinder, but it's a regular cylinder, right? This is also a solid cylinder, but it's not regular. See this triangular shape here, okay? There's this cutout on the bottom, which really actually doesn't affect anything. And then you have this mass sticking out at the end here, okay? So just to put all of this in together into one final blast. See, all these things go at once. And hopefully this works. The grand finale. This has the largest acceleration. This had the next largest acceleration. These two had the same acceleration, and this had the smallest acceleration. And it has to do, again, with the geometry. This is hollow. These are solid regular cylinders. This is also a solid cylinder, but notice that there is, if this was cut off right here, and so that's all we had, then that would be sort of identical to this. They'd both be solid cylinders. But here we have some amount of mass that is concentrated at the center, okay? So what we're looking at there is the difference in what's called the moment of inertia. You have seen or will see a video on the moment of inertia. The moment of inertia is the resistance to an object to its change in rotation. Just like regular inertia, which is usually called mass, the mass is a resistance to the change in the object's velocity, okay, or speed. And the rotational moment of inertia, the rotational mass, or the rotational moment of inertia, is a resistance to its change in rotational velocity or rotational speed. This has the biggest moment of inertia because all the mass is as far away from the center as possible. The moment of inertia for this system is simply the mass of this times r squared. Okay, the moment of inertia goes as the mass times the distance from the axis of rotation, which is the center of the tube. The mass times the radius squared. Because these both have the same moment of inertia formula, the moment of inertia of this, because it's solid cylinder, is 1/2 mr squared. Okay, where that comes from would be from some integration method that we don't necessarily need to worry about. But the moment of inertia for an object that has radius r would be 1/2 mr squared for this. For this, it would be mr squared, larger. And this, because some of the mass is closer to the center, it lessens the mass is larger because of the mass, but that mass is toward the center. So this is mr squared. This is 1/2 mr squared. This is even less because this much of it would be 1/2 mr squared. But this is reducing the moment of inertia because the mass that's here is located more toward the center, okay? Lowering the overall moment of inertia of the object. Now the radii are, of course, all different. It should be surprising, perhaps, that these, which have different radii, came down at the same rate, okay, with the same acceleration. The reason is that the radius in that equation will cancel. The acceleration of all of these objects as they move down this ramp is reduced by the moment of inertia. If the moment of inertia is larger, all right, the acceleration is reduced by more than if the moment of inertia is smaller. The moment of inertia, by the way, of this is 0. Okay, because, well, they have plastic here, but the mass of these plastic wheels is very small, so the moment of inertia of this is negligible compared to the rest of it. So this comes down due to just gravity. Now, what is affecting the acceleration? Because here we're talking about forces. What's affecting the forces here? The force of friction is acting. With gravity, there's a component of gravity down the ramp, making it accelerate. There's also a force of friction that's acting, but that force of friction is not acting over a distance. But what is that force of friction doing? The force of friction, let me explain here. This is a little bit larger, so I'll do this. The force of friction is acting at the base here. The force of friction is acting up the ramp. Whether it's moving up the ramp or down the ramp, the force of friction will be acting up the ramp. It is static friction. Okay, so you really can't tell what direction it's moving in. You can't tell what the magnitude of it is without doing a calculation because it's static. All right, it's not. If it was sliding friction, then as this slid up, friction would be down the ramp. If it slides down, friction would be up the ramp. But if it's rolling, whether it's rolling up the ramp or rolling down the ramp, friction will be up the ramp. Okay, so as this is sitting here, there's a force of friction up the ramp. So what's going to happen? That force of friction is going to cause this part to rotate in this direction. It's going to cause a torque in this direction, which will cause this thing to rotate. And how much does it rotate? It's going to have to apply more force to this because the moment of inertia is larger for this. This is the largest moment of inertia. Even though it's a lot lighter than the other objects, the moment of inertia is bigger as a formula, mr squared. Okay, so it will have to apply a larger torque. So the force of friction that acts on this will be bigger than the force of friction that acts on this. Okay, even though it's a static friction. But the force of friction will cause a torque which causes this to rotate in this direction, which allows this to then roll without slipping. Okay? The bigger the moment of inertia, the more energy goes into making this thing rotate.